Modern digital life depends on communication between people, apps, and devices that never meet in person. This video explains how public key infrastructure, or PKI, creates trust online, protects data, verifies identities, and prevents attackers from secretly tampering with traffic. By default, internet networks simply move packets. They don't prove who sent them or whether they were altered. This allows man-in-the-middle attacks, where an adversary silently intercepts and changes communications. Any trust online must be added on top of this untrusted foundation using cryptographic tools. Secure communication relies on three pillars. Authentication answers, "Who are you?" by verifying identity. Confidentiality ensures only intended parties can read the data. Integrity detects whether anything was changed in transit. Together, these pillars defend against impersonation, eavesdropping, and undetected modification of messages. Early systems used symmetric keys. The same secret key encrypts and decrypts data. If two people can somehow share this key securely, they get confidentiality and some integrity. However, securely distributing that secret to many users and proving each party's identity becomes extremely difficult as systems grow. Asymmetric cryptography introduces a key pair: a public key that can be shared freely and a private key that must be kept secret. The math links them so data encrypted with one can be decrypted only with the other. This breakthrough enables secure communication without pre-sharing a secret with every counterpart. For confidentiality, a sender encrypts a message with the recipient's public key. Only the matching private key, held by that recipient, can decrypt it. Even if attackers capture the ciphertext, they can't read it without the private key. This model scales well because public keys can be widely distributed without secrecy. Digital signatures reverse the roles. The sender signs data with their private key, producing a signature that anyone can verify using the sender's public key. Verification proves the data came from the holder of that private key and has not changed, providing both strong authentication and integrity guarantees. Public keys alone don't reveal who they belong to. An attacker can publish a key claiming to be someone else and trick others into encrypting or verifying against it. The lingering challenge is binding each public key to a real-world identity in a way everyone can independently trust. Digital certificates solve this by acting as cryptographic ID cards. A trusted certificate authority signs a document that includes a public key plus identity details, such as name, expiration date, and a unique serial number. Anyone who trusts the authority can then trust that the key truly belongs to that identity. Public key infrastructure forms an ecosystem around certificates. Policies, standards, and authorities govern how keys are issued, stored, used, and revoked. This framework underpins modern security models like Zero Trust, where every user, device, and connection must be authenticated and validated continuously before gaining access. PKI quietly powers everyday protections: HTTPS for secure websites, VPNs for remote access, encrypted Wi-Fi networks, and secure email. Each relies on certificates and key pairs to verify servers and users, establish encrypted channels, and prevent invisible tampering, protecting billions of transactions and interactions worldwide. Although the underlying internet cannot be trusted by default, PKI layers strong identity, confidentiality, and integrity on top of it. By combining asymmetric cryptography, digital signatures, and certificates issued by trusted authorities, organizations can confidently secure communications and enforce modern, high-assurance security models.